This is Lab 9, and today we'll be looking at a spring in constant motion moving from side to side. Basically, we'll be obtaining the oscillation on the x and y axis, and another important note is that no work will be done in surroundings due to the fact that everything is under the system, thus satisfying the energy principle delta E equals 0. As I stated, we're going to be looking at the motion of the spring in the x and y axis. So here we have the video obtained, and we're uploading on Tracker to get our experimental data, which we use to compare. And as you see, we have it set up as a normal system. Lengths and all of that is specified. So once we hit play, you can see it oscillate, and as you can see, we see the oscillation in terms of the x-axis. And if we click this button, we can see that same oscillation in terms of the y-axis, thus satisfying one of our main objectives for this lab. And as you can see here, we have a chart displaying it over time, which one could use to calculate the time period. After viewing data from the tracker, we can now look at our data extracted using Vital. As we can see, we have the x in terms of x, and we have it in terms of y. The red line represents the graph determined using Vital, and green represents the one we got from Tracker, and you see they're pretty dead on. And one could calculate the time period of the oscillation simply by taking the peaks and subtracting them. And for a time period, as you can see, we got about 0.627 and you see time period for y. As you can see, we have the y1 on the bottom right there. As you see, the red line once again representing the same thing. This one's a little bit off, but it's pretty precise measurement for the oscillation back and forth for Viato.
Hey, can you
As you can see, here is the code which we ran this data from. Some of the data is a runoff of some of the things we've extrapolated from the lab we did during class. So a lot of things are repeats. We graphed twice so that we have one in terms of x and one in terms of y. We have kinetic energy, and interesting enough, we have the work done, the potential energy of the spring, which is about 1.6. We have that calculation just using the equation we've gone over in class many times. This is the code. On top here, we actually have the actual time periods for the graph. As you can see, compared to the predicted one, they're not off, only by maybe fractions of a second. So that shows that our data is pretty accurate. And once again, this is calculated by taking the peaks of each of the curves and subtracting them from each other. So this from that. And while looking at this graph, one might ask, why is the oscillation for the x much longer than the y? And that's simply because the force of gravity acting on the spring is much stronger than the push that Greco gives in the x direction, thus causing it to spring back up faster in the y direction than to move from side to side in the x direction.
by 11. Sorry.
And here plotted is the graph of the potential gravity of the spring if y starts at 0. And here's a graph of the potential energy when one starts at its original. And as you can see, although it's quite hard to see, but if you see the axes, they're different, and that's because the delta y for the one that starts at 0 is much greater, thus increasing the potential energy by a great amount. And so it increases the energy within the system. However, if we start at the original coordinates, you see this much smaller delta y.